Okay, so in this video, we're going to take a look at European and American option valuation, and we're going to use the binomial framework, and that's Cox, Ross, Rubinstein, and at least initially here, Lyson-Reimer. Cox, Ross, Rubinstein is the more well-known of the two binomial frameworks, and it converges to true. But it at a low step size, Lyson-Reimer tends to be a little bit more accurate. Okay, so we're going to copy this code. If you want an introduction to Cox, Ross, Rubinstein, I would advise click on this link. It's based on John Hull's textbook, Option, Futures and Other Derivatives, his explanation of the Cox, Ross, Rubinstein lattice and just basic setup. And also important more on from the operations research side here is how do we build these type of structures? So what are the dynamics in terms of passing values between nodes in a binomial framework, and that you will find here clicking this link. So we have copied this segment of code. Then very simply, we go into a compiler. Fortunately, online GBD is we can use it for Python or C++ or Java and so on. We're going to designate the C++ implementation here. We delete out the code and we paste what we copied. And we might take a look at the parameter values. We might reduce that to 100 steps. This is for Cox, Ross, Rubinstein. The value of U is EV multiplied by square root of the change in the time step. And then the risk neutral probability is consistent with the Cox, Ross, Rubinstein risk neutral probability. Okay, so we can run this, but we just note it's a spot price 100, exercise 100, maturity 1 year, dividend is 5%, risk-free rate is 0, and the volatility is 20%. That should produce a European call value of 1045. But we're going to get the call, the put for both the European and American options. And if we come down here and inspect the numbers, you can see that again, let's just check our numbers. We should have got 1045. So 100, 100, 1 year, 5%. Okay, so we changed this dividend to 0 and the risk-free rate should be 5. Let's execute. And the European call should be 1045. We're getting 1043, but that's because the step size is not so high. The European put should be 557. We're about 2 cents out. The American call and European call are the same because dividend is 0, so not optimal to exercise early. But the European put is worth more than the American put is worth more than the European put because it is optimal to exercise early in that instance. If we raise this to 1,000 and run again, we'll get values that are closer. So it should be about 1045. We get 1044.86, so that's approximately 1045. Again, same value for European and American calls. European put 557, that's consistent with Black-Scholes. American put a little bit higher, quite a bit higher, I suppose. So it is optimal to exercise early. Okay, so that's quite practical then. One thing we could take a look at here is just examine for a moment, if we go to the next link, come down to, this is table 2 of Brody and Temple 1996. There's a link somewhere in the portal to the original paper. We can have a look at that later on. If we can remember, the parameter values here, K, the exercise 100, spot price 100, R 3%, dividend is 7, volatility 20. And if we go that step size, we observe we get a value of 9.066 is true, and true is based on a 15,000 step tree. So the true value is based on the 15,000 step tree. Now, 15,000 step tree with static utilization of memory is not going to be that efficient, but we can, those values are the same. We should change the maturity to 3 years. If memory serves correct, the dividend was 7. The risk-free rate was 3, and the volatility was 20%. And if that's correct, the American call is equal to 9.066. So we'll have a look at what we have here, and we do get a value that's quite close. Now we can raise this to 2,000, and maybe we get a little bit closer. So we're looking to just verify that we're converging. And as we increase the number of steps, we more than double. If we double the number of steps, we more than double the time it takes. And now we're getting 9.065. So we are getting a little bit closer. Okay, so this looks quite good. And again, when we compare with the Black-Scholes values for the European, this option, this methodology looks as if it's reasonably accurate. Okay, so I'm going to stop here with this segment of Cox-Ross-Rubinstein code. Looks quite good.